capacitor B here. So by this example, folks, this is not the complete circuit. This is just like one part of it to show it to you. Now, optimally, what would be nice here is eventually to have an additional switch, which I don't have here, to feed back this additional energy back into the input at some point. Or else what's going to happen here is in this state, I'm eventually going to have to manually start flipping capacitors around. But for the sake of showing the effect, it's good enough for now, and even for anyone to experiment with on their own. So to start here, this is capacitor A over here. It's 500 F, and it can handle 2.7 volts. Same capacitor here. So I charged this one at 1.96 beginning. This one was discharged, okay? So what I decided to do is I just found a random power supply transformer I had around the house. This is an AC to AC, 110 to 2 volt AC. So what I've done is I've connected it in reverse, so the low voltage side is completing the path. So I'm doing a switch here. So right now I'm switching it at Hertz, which was the optimal. And what happens is I start off at 1.96 volts here, and impulses, it's charging it here. So we're not actually wasting the energy, we're transferring it from this capacitor into this capacitor. So sure enough, because these are very high farads, after about an hour, this one dropped to like 0.01 of a volt, while this one went up around the same time at 0. of a volt or so, you see. So what I'm getting at is whatever percentage dropped out of this one, I saw back in this one. So of course maybe minus 10% losses or so, but all in all, what I'm getting at is we're just transferring, with the help of the switch, the charge from here to there. And the displacement current is what's actually rectifying this full bridge rectifier here. And this is charging a set of 10,000 farads, okay? So there's a big difference here between 500 and 10,000, okay? So this has been running now, and these were set to 0, you see? So now we're already at 2.51 volts. So there's definitely more here than there was when I started, okay? And this is very efficient because these are very high farad capacitors, it takes a while to this. What I'm getting at, folks, is if you use too high farads, if you're not discharging it into a load or a short, the capacitor is limited by its own inherent like internal resistance, so how fast it could accept the charge. So it's like how you charge a supercapacitor and it could take 10 minutes on a power supply, because you know it takes more than 1 joule of energy in one shot to recharge these. So the same thing applies if you were to take a fully charged one and try and charge it direct. You'd still have to wait a few minutes for it to successfully transfer over. It's not instantaneous like we normally would expect out of capacitors, because these are just so powerful capacitors. So what happens is the dynamics are a little bit different with supercapacitors. It simulates through the transformer basically a steady state. So what happens if it's a steady state, you need a time varying effect in the field to be able to induce a voltage on the primary, right? So in order to create this effect, we need to use a switch to chop it up so that it simulates basically an AC effect with the displacement current. All this does is actually slow down the charge from here to here. It doesn't actually eat it up or anymore, but it allows us a compatible signal to hit. This happens continuously, and as you see, there's a massive gain here. Now obviously at high voltages, things change here. You can squeeze a lot more joules with a lot less capacitance. So you increase the high voltage like Don Smith does, shrink the capacitors down massively, and if you calculate it right, you could figure out an area where one inherently directly discharged to the other will last much less than a second and distribute that full energy. Now what happens is, let's say your discharges are 50 milliseconds or less at high voltage. Well, if you pass that through a transformer that's suitable for it, then you're simulating the same AC-like effect without having to control the switching discharge slowly like we're doing here. But ultimately you end up with the same effect, and some would arguably say that high voltage dynamics offers more efficient transfer of energy. So in part that's why Don Smith decided to use high voltage, but there's no specific rule that tells you it has to be high voltage interaction. You can see it going up there even more. Now, Don Smith even hinted that, oh, you could do it with 5 volts and a supercap without getting into the details and still get a high output. Well, here's the demonstration. So this is just running the switch here. Now, I know what you're going to say, folks. Oh, it's being powered by the switch. The switch is leaking. It's not free energy, blah, blah, blah. Well, you know what, folks? Before I put the switch, I did it manually by doing this to it for 5 minutes. And then I observed until the charge started coming up. Then when I confirmed it was working, I said, I'm getting tired with my hand here. So I'm just going to automate it for a switch for now just to observe the effect. And obviously the next step here would be anyone who wants to do this to scale it up to what they need. Obviously build the proper transformer to match the capacitors you're using with. And obviously that would run the switch, folks. You can see there's a massive gain here. But I just want to tell you that it's not coming from the switch. You can do this experiment yourself, and please do tap it manually, no switching through a transformer. Rectify that, and that'll charge a bigger capacitor. So I just wanted to show you the example. There's nothing connected there. That's why I wanted to show you in case someone says, oh, it's his magic box. It's all disconnected. So the switch here is only pulsing this.
So I'm sure you've seen it. I hope it was audible.
So what exactly was the driving point there? That he's charging capacitors?
Yeah, yeah. Like Network Metatron wanted you to know the issue to do with supercapacitors. He was talking that you can induce, was it current, more current, by trying the back EMF. When we started the conversation, we were talking about Lovell's what Lovell showed, where he was able to increase voltage, but he wasn't showing the current. And you say the current might be in something microamperes, which won't help with anything. So then Network Metatron came in and say that it has been proven that by using the supercapacitors, there was this comment somewhere here. Let me try to get it. And he said that he can prove it to you. He can show you a video. So he shared the link of that video. He
All right.
said,
So again, I'm only interested in what's being biased and where's the power coming from. That tells me the whole story. So you can pass it to capacitors all you want. I can tell you that whatever charge you put in that capacitor came from a power supply somewhere, so a source of energy somewhere. That back EMF came from a source somewhere. You can't have back EMF unless that inductor is charged. And if that inductor is charged and you turn that thing off, it's going to reject that turning off and it's going to flip polarity. That's where the spike comes from. But it doesn't do it if there's no energy in the coil. That's where it comes from. Energy you already put there. I don't know why this is like really hard to explain more than that. So, I mean, Lloyd's telling me he's doing back EMF without even a coil. I